Welcome to today's discussion. We'll be exploring a fascinating research paper titled AFLOW, Automating Agentic Workflow Generation. This paper tackles the challenge of automating the creation of workflows for large language models, LLMs. What's the core problem this research addresses?
Certainly. AFLOW, which stands for Automating Agentic Workflow Generation, is essentially a smart assistant for AI systems. Imagine you're trying to teach an AI to solve complex problems. Normally, you'd have to manually design a step-by-step guide for the AI to follow. AFLOW automates this process, creating these guides or workflows on its own.
Why is this automation so crucial?
It's crucial because manually designing these workflows is time-consuming and limits how quickly we can adapt AI to new tasks. By automating this process, AFLOW allows AI systems to be more flexible and efficient, potentially revolutionizing how we approach complex AI tasks.
How does AFLOW aim to overcome this limitation?
AFLOW reformulates workflow optimization as a search problem. It represents workflows as a network of interconnected nodes, where each node represents an LLM action and the edges define the relationships between these actions. This allows AFLOW to explore a vast search space of possible workflows.
Can you elaborate on why this is beneficial in layman's terms?
Absolutely. Think of the code representation like a very detailed recipe. Just as a recipe can include instructions like, if the dough is too dry, add more water, the code can include complex instructions and decision-making processes for the AI. This allows for much more sophisticated and adaptable workflows compared to simpler representations.
That makes sense. The paper mentions operators and Monte Carlo tree search. What roles do these play in AFLOW?
Operators are like pre-built Lego blocks that AFLOW can use to construct workflows. They represent common AI operations that we know work well. By using these operators, AFLOW can build complex workflows more efficiently without having to reinvent the wheel each time. Monte Carlo tree search, or MCTS, is like a smart trial and error process. Imagine you're trying to find the best route through a maze. MCTS would try different paths, learn from its attempts, and gradually focus more on the promising routes. This allows AFLOW to efficiently explore the vast number of possible workflows and find effective solutions.
Interesting. Now, the paper claims significant performance improvements. Can you put these results into perspective for our listeners?
Certainly. AFLOW consistently outperformed existing methods across various tasks, with an average improvement of 5.7%. But perhaps more impressively, it enabled smaller, less expensive AI models to outperform larger, more costly models like GPT-4 on specific tasks. This is like a skilled amateur chef with basic ingredients outperforming a professional chef with premium ingredients. It shows the power of having the right recipe or workflow.
How does AFLOW handle the exploitation trade-off in its search?
AFLOW employs a clever method called a soft mixed probability selection mechanism to effectively balance exploration and exploitation in its search for optimal workflows. This approach combines two strategies. First, it gives every possible choice an equal chance, uniform probability distribution, allowing AFLOW to try new options randomly and discover unexpected breakthroughs. Second, it favors choices that have proven successful in the past, score-based weighted distribution, ensuring that it often relies on strategies known to work well. By mixing these two approaches, AFLOW achieves a balance that enables it to explore new possibilities while also capitalizing on effective solutions, ultimately leading to more efficient and productive workflow generation.
The paper mentions an early stopping mechanism. Why is this important?
Early stopping prevents unnecessary computational cost. The algorithm stops iterating when the top-performing workflows show no significant improvement for a certain number of consecutive rounds.
What are some limitations or future directions for this research?
While AFLOW shows promise, further research could explore more sophisticated search algorithms, more complex operator sets, and applications to a wider range of tasks and domains. The current implementation simplifies the search space by fixing certain parameters. Relaxing these constraints could lead to even better performance.
The paper mentions an ablation study. What did that reveal?
The ablation study, removing the predefined operators, showed that AFLOW could still discover effective workflows even without this human-designed guidance. It even autonomously developed structures similar to ensemble methods, highlighting its ability to learn effective strategies independently.
Fascinating. It sounds like AFLOW could be a game changer in the field of AI. Thank you for breaking down this complex research into such accessible terms for our listeners.
It's my pleasure. AFLOW is indeed an exciting development, and I'm glad I could help explain its potential impact. As AI continues to evolve, tools like AFLOW that can automate and optimize AI processes will likely play a crucial role in shaping the future of artificial intelligence.